Hi, I'm the Wannabe Coder, and welcome back to the Pac-Man and Python series. This is episode 8, and in this one, we're taking a big leap forward. By the end of this episode, our game will be fully playable, with all the core logic in place. So far, we've built the maze, set up Pac-Man and the enemies, and added pellet collection with a scoring system. In this episode, we'll give our enemies some basic AI, so they actually chase Pac-Man when he's nearby. We'll add a short delay before the game starts, so the player has a moment to get ready. We'll make sure Pac-Man never spawns too close to an enemy. Not at the start, and not when he respawns. And finally, we'll handle the end of the game. Whether the player wins by collecting all pellets, or loses all their lives, we'll display a final message and close the game. But before we jump in, let's quickly recap what we did in episode 7. In the last episode, we introduced the ghosts, the first real challenge in our game. We created a brand new enemy class, gave each ghost a random starting position, and added basic movement so they could roam the maze freely. We also added wall collision logic, so the ghosts bounce off walls and change direction when they hit one. And to make things more intense, we added player-enemy collisions. Now, whenever Pac-Man touches a ghost, he gets teleported to a random spot and loses one life. To start off this episode, we're going to tackle the first feature, enemy AI, by giving the ghosts the ability to follow Pac-Man. Let's first understand the logic behind it. We'll create a new method inside the enemy class that checks the distance between the ghost and the player. If Pac-Man is close enough, about 5 tiles away, the enemy will turn to face his direction. This lets the ghosts actively chase the player, especially when they're near an intersection, making the game feel a lot more dynamic. So, let's jump into constants.py and define a new parameter called enemy_radar. We'll set it equal to cell size times 5. That means whenever a ghost is within 150 pixels of Pac-Man, it'll start tracking and adjusting its direction. Now, let's head over to actors.py and give our enemy class a few final touches. First, at the import section, we update the line that imports values from constants. We add enemy_radar to the list. Next, scroll down to the enemy class. To let each ghost follow Pac-Man, it needs to know where he is. So we'll pass the player into the enemy's init function. Inside the parentheses, after walls, we add a comma, then write player:player. This passes the player object to the enemy when it's created. We'll also change self.state to stop so that enemies don't start moving right away. This will let us add a short delay at the start of the game. Now, right after that, we add a new line, self.player=player. This line stores the player object inside the enemy instance, so the ghost can access Pac-Man's position later, when we build the logic for chasing him. Now, scroll to the end of the enemy class, and let's define a brand new method called goAfterPlayer. This will give the enemy a basic form of artificial intelligence, so it can follow Pac-Man when he's nearby. We'll start with defgo_after_player, open parentheses, self, close parentheses, colon. Inside the method, we'll round the positions of both the player and the enemy, so they snap cleanly to the grid. We store them in 4 variables, player_x, player_y, enemy_x, and enemy_y. Each one just calls the x-core or y-core function, which returns the center position of the object and wraps it with round to keep things aligned to the tile grid. Now let's look at the first condition inside the method. This handles left and right movement for the enemy. We write, if, open parentheses, self.get_heading equals 0, or self.get_heading equals 180, and self.distance to self.player is less than or equal to enemy_radar, close parentheses, colon. Let's break that down. Self.get_heading returns the current direction the ghost is facing. We check if it equals 0, which means the ghost is moving right, or 180, which means it's moving left. Then, we use the and keyword to add another condition. Self.distance, open parentheses, self.player, close parentheses, calculates the distance between the ghost and Pac-Man. We check if it's less than or equal to enemy underscore radar. So this part makes sure the player is close enough to trigger a reaction. Only if both conditions are true, the enemy is moving horizontally and Pac-Man is nearby, we continue into the next check. This one determines if Pac-Man is above the ghost and whether they're nearly in the same vertical column. We write, if, open parentheses, player underscore Y is greater than enemy underscore Y, and player underscore X plus cell size divided by 2 is greater than enemy underscore X, which is greater than player underscore X minus cell size divided by 2, close parentheses, colon. Let's break that down. First, player underscore Y greater than enemy underscore Y means Pac-Man is physically above the ghost on the screen. Then, we check for X alignment to see if they're on nearly the same vertical path. The expression player underscore X plus cell size divided by 2 is greater than enemy underscore X checks if the ghost is not too far to the left of Pac-Man, and enemy underscore X is greater than player underscore X minus cell size divided by 2 checks if the ghost is not too far to the right. So together, these two X checks mean the ghost is within half a tile's width of Pac-Man's X position, and if all that is true, we write self.setHeading 90, which tells the ghost to turn up toward Pac-Man. Now let's look at the next condition. This one checks if Pac-Man is below the ghost, but still aligned closely on the X-axis. We write L if, open parentheses, player underscore Y is less than enemy underscore Y, and player underscore X plus cell size divided by 2 is greater than enemy underscore X, which is greater than player underscore X minus cell size divided by 2. Close parentheses, colon. Let's break that down. First, player underscore Y less than enemy underscore Y tells us that Pac-Man is underneath the ghost on the grid. Then we have the same X alignment checks as before, just like in the previous condition. The first one, player underscore X plus cell size divided by 2, is greater than enemy underscore X, means the ghost isn't too far to the left. And the second one, enemy underscore X is greater than player underscore X minus cell size divided by 2, means it's not too far to the right either. So if Pac-Man is below and their X positions are close, we write self.setHeading 270, which tells the ghost to turn down to follow Pac-Man's direction. Now, we switch to the second part of the logic, this time for when the ghost is moving vertically, either up or down. We follow the same structure as before. First, we check if the ghost's heading is either 90 or 270, which means it's moving up or down. We also make sure the player is still within radar range. If both of those are true, we then check if Pac-Man is to the right or left of the ghost, and whether their Y positions are nearly aligned, meaning they're on the same horizontal row. If Pac-Man is to the right, we set the heading to 0, so the ghost turns right. If he's to the left, we set the heading to 180, and the ghost turns left. Just like before, we use half a tile's distance as the threshold to make sure the turn only happens when Pac-Man is close and aligned. So here's what we have so far. This function, go underscore after underscore player, lets the ghost detect when Pac-Man is within 5 tiles and turn toward him when approaching an intersection. That's a big upgrade because now the ghost can make decisions before hitting a wall, which makes their movement feel smarter and more responsive. Now, let's move on to the final part of the function. In this last section, we handle cases where Pac-Man and the ghost are already moving on the same row or column in the same direction, with no intersections in between. This logic ensures that if Pac-Man is within radar range, even on a straight path, the ghost will adjust its heading to keep chasing him directly. So let's take a look at how that works. We write if player underscore y equals enemy underscore y and player underscore x is greater than enemy underscore x and self.distance to self.player is less than enemy underscore radar, colon. This condition checks if Pac-Man is on the same horizontal row and to the right of the ghost within radar range. If so, we set the heading to 0, so the ghost turns right. The next condition does the same, but for when Pac-Man is to the left, in that case, we turn the ghost left with a heading of 180. Then we check for vertical alignment. If they're on the same column and Pac-Man is above, we turn up with a heading of 90. And if Pac-Man is below, we turn down with a heading of 270. This ensures that even when the ghost is already on the same path and there are no turns involved, it will still follow Pac-Man directly if he's close enough. That completes our enemy tracking logic. Now let's switch over to main.py to start using this method, and make a few more important tweaks to bring our game closer to the final version. Scroll down to the main function, to the section where we create our enemies. Right now, when we create each enemy, we're passing in just the starting coordinates and the walls. But now that the enemy class needs access to Pac-Man, we also need to pass in the player. So, in the line where we create the enemy object, inside the parentheses of the enemy call, right after walls, we add a comma, then pass in the player. This way, each ghost will have a reference to Pac-Man, so it can track and follow him during gameplay. But before we jump into the game loop and start calling that method, we're going to set up a better game start experience. We'll do two things. First, we'll make sure Pac-Man doesn't spawn too close to any enemies at the start of the game. To do this, we'll give him a kind of safe zone, a minimum number of tiles away from the ghosts when they're first placed. This helps avoid unfair collisions as soon as the game begins. Second, we'll add a short screen delay so that when we run the game, it doesn't start immediately. Instead, we'll display the maze for a couple of seconds, then let the ghosts start moving. That's actually why we set the enemy's state to stop earlier, because when the delay is over, we'll call the start_move method, which changes the state to move and allows the ghost to begin chasing Pac-Man. To make the enemies start far away from Pac-Man, here's what we're going to do. Inside the loop where we create the enemies, just under the line for underscore in range, enemy underscore number, we create an empty list by writing safe underscore spots equals open and close square brackets. This list will store only the pellet positions that are far enough from the player. Now, under that line, we loop through all the pellet coordinates by writing for pellet in pellets, colon. Inside this loop, we check the distance from Pac-Man to the pellet by writing if player.distance to pellet is greater than cell underscore size times 5, colon. This means if the pellet is at least 5 tiles away from the player, we consider it safe. So, inside that condition, we add the pellet to the list by writing safe underscore spots dot append open parentheses pellet close parentheses. Now that we have a list of safe starting points, we update the enemy's spawn position. Instead of choosing a random pellet from the full list, we set the enemy's starting coordinates like this: enemy underscore start underscore x, comma, enemy underscore start underscore y equals random dot choice, open parentheses, safe underscore spots, close parentheses. That's it. This guarantees that each enemy starts at least 5 tiles away from Pac-Man. Now let's handle the delay at the start of the game. We're going to add a short pause so the player has a couple of seconds to get ready before anything starts moving. And we'll also delay the keyboard bindings, so pressing arrow keys during the delay doesn't do anything. Here's what we do. First, make sure to delete the original call to bind underscore controls. We don't want it to run right away. Then, we add a delayed version using the screen timer. We write screen dot on timer, open parentheses, lambda colon, bind underscore controls, open parentheses, screen, comma, player, close parentheses, comma, 2500, close parentheses. This tells the game, wait 2.5 seconds, then run the bind controls function with the screen and player parameters. Without this delay, if you press an arrow key the moment the game starts, it won't work, because the controls haven't been bound yet. So this line makes sure keyboard input is only activated after the short delay. Now let's do the same for the enemies. We'll delay their movement so they don't start chasing Pac-Man immediately. Right after the line where we delay the control bindings, we loop through each enemy and set a timer. We write, for enemy and enemies, colon, screen dot on timer, open parentheses, enemy dot, start underscore move, comma, 2500, close parentheses. This tells the game, wait 2.5 seconds, then call the start move method for that enemy. Since start move doesn't take any parameters, we don't need to wrap it in a lambda. We can pass it directly to on timer. This keeps the code simple and clean. Until the timer runs out, the enemy stays still, because its state is set to stop by default. Once the timer finishes, the ghost state becomes move, and it starts chasing Pac-Man. Now, we can finally scroll up to the game loop function. Find the section where we loop through each enemy in the enemies list. Inside that loop, we already call methods like move and check wall collision. Now, right after the line that calls check wall collision, we add one more line, enemy.go underscore after underscore player, open and close parentheses. This is what actually makes the enemy start chasing Pac-Man in game. It checks the distance between them and decides whether to turn toward the player based on the logic we wrote earlier. Alright, let's run the file and see it in action. You should now see each ghost react to Pac-Man when he gets close, and change direction at intersections to follow him. The game might feel a lot more challenging now, which is exactly what we wanted. But if it feels a bit too hard, don't worry. You can always go back to the constants file and tweak some of the parameters. You can lower the number of enemies, adjust their speed or Pac-Man's speed, or change the enemy radar value to control how early they start chasing you. Feel free to tune it to match your own playstyle. Now, let's go back to the game loop function and add a couple of final gameplay tweaks. First, we want to make sure that when Pac-Man loses a life, he respawns at a safe spot, just like at the start of the game. We don't want him to reappear right on top of an enemy or even on a tile that's too close, because that would be unfair and could cause an instant game over. To make Pac-Man respawn safely after a collision with a ghost, we'll add a bit of logic right inside the condition where we detect that the enemy is close to the player. Here's what we'll do. First, we create an empty list to store safe positions. We write safe underscore spots equals open and close square brackets. Then, we loop over the available pellet positions. These are all valid tiles in the maze. We write, for pellet in, pellet underscore pen dot pellets, colon. Now comes the important part. We want to make sure that the pellet we're checking is far enough away from every enemy. So, inside the loop we write, if all, open parentheses, enemy dot distance to pellet is greater than cell size times 5 for enemy and enemies, close parentheses, colon. Let's break that down. All is a built-in Python function that checks every condition in a list and only returns true if all of them are true. Inside the parentheses, we're using what's called a generator expression, which is just a compact loop. Let's look at the part. For enemy in enemies. This means we're going to loop through every ghost in the enemies list. Then for each ghost, we check this condition. Enemy dot distance to pellet is greater than cell size times 5. In other words, is this pellet at least 5 tiles away from each enemy? If all of the ghosts are far enough, we say this pellet is safe, and we add it to the list by writing safe underscore spots dot append, open parentheses, pellet, close parentheses. Finally, we randomly choose one of those safe tiles and send Pac-Man there using player.goto, open parentheses, random.choice, open parentheses, safe underscore spots, close parentheses, close parentheses. This guarantees that Pac-Man always respawns in a safe location, not too close to any ghost, even in the middle of gameplay. Now, let's handle what happens when the game ends. There are two ways that can happen. Either the player wins by collecting all the pellets, or loses by running out of lives. Let's start with the win condition. If Pac-Man eats every pellet on the screen, that means the player has completed the level. So here's what we'll do. We'll hide all the enemies and set their state to stop, so they stop moving completely. Then we'll wait a couple of seconds and use a built-in function to close the game window. That gives the player just enough time to see that they've won before the game ends. Now for the lose condition. If Pac-Man's lives drop to 0, we want the game to stop right away, but still give a moment to show what happened. So here's what we'll do. We'll set the state of all enemies to stop, just like before, and Pac-Man as well. Next, we'll hide Pac-Man from the screen, so it's clear that the game is over. And finally, we'll wait a few seconds, and then close the game window to end the game. Now, let's go back to the game loop function and add both of these checks. First, the win condition. We write if length of power underscore pen dot stamps equals 0 and length of pellet underscore pen dot stamps equals 0, colon. This checks if all the pellets and power pellets have been eaten, because both lists are now empty. If they're both gone, the player wins. So we stop the player's movement by writing player.state equals stop. Then we loop through each enemy and write enemy.hideTurtle and enemy.state equals stop. This hides the ghosts and stops them from moving. And finally, we close the game window after a short delay. Screen.onTimer, open parentheses, screen.by, comma 3000, close parentheses. That gives the player 3 seconds to see they've won before the game ends. Now, the lose condition. If the player's lives reach 0, we do almost the same thing. But instead of hiding the enemies, we hide Pac-Man. We stop his movement, hide him from the screen, stop the movement of all the enemies, and then close the game window after the same 3-second delay. We close the game window by using the built-in turtle function, by. This function closes the game window. We write screen.by, and we wrap it inside screen.onTimer with a 3 seconds delay. That's how we handle both game-ending scenarios, whether the player wins or loses. Now, let's add the final touch to our game, a message that appears at the end, telling the player whether they won or lost, along with their final score. To do that, we'll scroll up to the start of the game loop function, where we already call score underscore pen dot write underscore score and lives underscore pen dot write underscore lives. Right now, these functions just display the current score and number of lives, but we want to update them, so they also know when the game is over. To make that happen, we'll pass a couple of extra values into these method calls. First, for score underscore pen dot write underscore score, we'll pass in player.lives, the list of pellet stamps, and the list of power pellet stamps. This way, the score function can check, are there any pellets left, and is the player out of lives? Next, for lives underscore pen dot write underscore lives, we'll pass in the same 2 lists, so that method can also check if the game has ended. This gives the player a satisfying ending, and wraps up the game with a clean message on screen. Let's go ahead and implement it. To do that, let's first head over to renderer.py. Inside that file, we're going to update the write score and write lives methods to display these messages when the game ends. Let's start with write underscore score. We added a few new parameters to the function, lives, pellet stamps, and power stamps. These give the method everything it needs to know when the game is over. Inside the function, we added two simple checks. First, if lives are 0, we clear the score display, change the color to red, and write "Game Over" and display the final score. Then, we check if the player has won the game. If both pellet lists are empty, that means all the pellets were eaten. So we clear the score again, change the color to yellow, and display "You won." Right after that, we show the player's final score. Now let's look at write lives. We added the same 2 pellet lists as parameters. Then, at the end of the method, we check if the game is over, either because lives reached 0 or all pellets have been collected. If so, we simply clear the lives display by calling self.reset. This resets the turtle object, it clears the text, hides the pen from the screen, and sends it back to its default position. That's it. Just a few lines of code to clean up the screen at the end and give the player a satisfying final message. All right, let's save the file, run the game, and see it all come together. At this point, we've built a fully playable Pac-Man clone. We've got a working maze, Pac-Man movement with wall collisions, pellets and power pellets that update the score, enemies that move through the maze and chase Pac-Man when he gets close, collision logic that makes Pac-Man lose lives and safely respawn, a short delay before the game starts, and a proper endgame screen that tells you if you won or lost and shows your final score. It's simple, fun, and all done with Turtle graphics in Python. Try it out, and tweak the constants if you want a harder or easier game. Let's do a quick recap of what we built in this episode. We gave the ghosts a simple AI so they can chase Pac-Man when he's nearby. We made sure Pac-Man respawns safely, added a short delay before the game begins, and displayed a clear message when the game ends, either with a win or a game over. In the next and final episode, we'll add the finishing touches by introducing custom graphics and sound effects. We'll load in new shapes for Pac-Man and the ghosts, and we'll play sounds when the game starts, when Pac-Man eats a pellet, and when he gets caught by a ghost. If you found this helpful, a like and subscribe would really help support the channel, and make sure you don't miss what's coming next. I'm the Wannabe Coder. Thanks for watching, and I'll see you in the next episode.